In this video I'm going to talk about state machines, which is a common pattern in embedded systems and in programming overall. And as with other patterns, it's a way to break down a system into smaller parts, and in the case of a state machine we break down the system into a set of states and transition between these states when an event occurs. For example, if I take this smartwatch that I got here, you can imagine that normally when I'm not using the smartwatch and it's just sitting on my hand, the display is turned off and it's in some sort of low power mode. But as soon as I press a button, it's going to wake up, and you can see this button press as an event that takes the smartwatch from a low power state to a more active state. And then if I go into the menu and try to change the settings, you may represent that as another state. This is probably not how it's implemented in this smartwatch, but you kind of get the idea. State machines are a big topic and there are many ways to implement them. They can be simple and they can be complicated, and there are libraries and tools to help you implement them, as well as entire books written about them. And I'm not an expert on them. So as I usually do in my videos, I'm going to keep things simple and practical by demonstrating the topic through my limited knowledge and project. And the project is this sumo robot that I've been covering throughout this video series. And as I've told you before, the goal with this system is to act as a sumo wrestler. It's going to be placed on a circular platform, and it should find the other sumo bot and then push it out of the platform in order to win. And I'm now going to break this system behavior into a set of states and transitions before I move on to implementing the actual code. Note, I will have to write quite a lot of code for this, so I'm not going to write all of it in this video, and instead in this video I'm going to focus on getting the skeleton code in place, like the overall structure, and then in the next video I will finish the implementation by filling in the details and show that it works in the simulator I showed you in the last video, and then also show you that I can run it on the actual robot. And to create diagrams like these, I like to use a tool called PlantUML, which is an open source tool that lets you generate diagrams from plain text, which makes the diagram easy to modify and also version control. It's also good at creating sequence diagrams, so overall a good tool to have in your documentation toolbox. And in order to use PlantUML, you need to have Java installed on your machine and also download a jar file from the official website. And depending on the type of diagram you want to generate, you may also need to install something called GraphWiz. And then you can run this command in order to generate the diagram as an image file. Okay, and since this is related to documentation, I'm going to create my plain text file under my docs folder, and I'm going to call it statemachine.uml. And then the plain text syntax I use is also explained on the official website, so I'm not going to explain it here, but each file has to start with @start.uml and end with end.uml. And then I'm just going to add an option at the top to hide empty description, just to make it look a bit nicer if I don't have a description inside my state. And then I can start by filling out the main states that I will have in my state machine. And overall I think this system, or this sumo robot, is a pretty clear-cut case for a state machine, because the behavior can easily be divided into different states by simply thinking conceptually about what the system is going to be doing. So at the start, my sumo robot is going to be placed on the platform, and then it's going to wait for a start signal to be sent from an IR transceiver. In my case, that's going to, or at least during development, that's going to come from this IR mode, which I've already written a driver for previously in this video series. So I'm just going to have this first state, and I'm going to call this state wait, or as wait, and then I'm going to add some additional description for this state. And since this is the starting state, I'm also going to add this at top here. So let's try to generate this diagram now. I can move this over. And then I can just view it with an image viewer. So this is just what it looks like so far. And then once my SumoBot receives the start signal, it's going to start searching or trying to find the enemy it's meant to push out of the platform. And I'm simply going to call this state search and add this in a similar manner as to the other state, with a description as well. And then when my SumoBot detects the enemy, it should drive towards the enemy, and I'm going to call this state attack. But there is also a surrounding white border around the platform, and as soon as my SumoBot notices this white line, it should drive away from it in order to not drive out of the platform by itself. And I will have to represent this as yet another state, and I will call this state retreat. And this retreat state is going to be the most complicated state, and I will create another diagram for this in order to not clutter up the diagram I have here. And these are actually the only states that I will need to represent my system here. But I'm also going to add another state for debugging purposes, which is a state where I will be able to control the sumo robot manually with this IR remote. And that's just a thing that is nice to have during development. And I will call this state manual, because in this state I will be able to manually control the behavior of the sumo robot. So if I then generate this diagram again and open it again, you can see that all of the states are available now. Of course, doing it like I do it here now, where I open the image viewer each time, is a bit tedious. And I know there are some like live viewers that you can use for PlantUML, but for this video I'm just going to do it like this. Next, I need to define the different events that's going to cause this state machine to transition from one state to another state. So beginning with the wait state, the only reason it's going to transition from this state is if it receives a command from this IR remote, and then it should transition to the state search. So I'm going to call this event command, and I can add a transition like this. So dash dash arrow and then search and then the event. So if I generate this, I have some issues here, so I think I will just remove the diagram first and then I will regenerate it. So like this, and then at the end I can also open the image viewer. Okay, I have the wait state, and then if I receive a command, I'm going to transition to the search state. And then inside the search state, while the sumo robot is searching for the enemy, there can be several different things that can happen and take it to another state. First of all, if it detects the enemy, it should transition to state attack. And I will add a new line here in between to make the drawing a bit tighter. But in the search state, it could also be that it detects the white border, and then it should instead transition to the retreat state. So if it detects the line, it should transition to retreat. Inside the search state, I'm also going to have two substates. The robot is going to either be rotating to see if it can find the enemy, and if it rotates for a certain amount of time, it's going to time out and transition to another state where it simply just drives forward. And this is going to be my simple search strategy. I'm going to add two new substates to the state search. So one state where it's rotating and another state where it's driving forward. Then I can add a transition between these as well. And it's going to transition between these internal state when a timeout happens. So I'm going to add that here, so transition to itself and timeout. And finally, if it's in the search state and I press a button on this IR remote, I want it to transition into the manual state so that I can control the robot manually, like that. So now I can generate this diagram again. And now it looks like this. So we start in the wait state, and as soon as we receive a command, we're going to transition to the search state, and then depending on what happens inside the search state, we're going to transition to these other states here. So that's it for the search state. Moving on to the attack state, this is going to be similar. If we are in the attack state and we detect the enemy, we should still be inside the attack state. But similarly, if we detect the line, we should transition to state retreat. And if we are in the attack state and we suddenly lose sight of the enemy, we should transition back to state search. And in the state machine, I'm going to represent this as event none. So if nothing happens, it means that we no longer detect the enemy and we're not detecting the line or nothing else is happening. I'm just going to say none here. And then in that case, we're going to transition back to state search. And if I press the key on the IR remote, it should transition to state manual. Command, generating this again. It looks like that. And in state attack, I'm also going to have internal substates, 3 substates. This is just going to make the robot drive a bit differently depending on where it's locating the enemy. So whether it's seeing it slightly to the left, slightly to the right, or straight in front of it. So like that. And then I'm going to have these 3 choices here originate from a choice. And if I regenerate this, it's going to look like this. So now we get to attack state, and then depending on the detection we have made, it's going to transition to either substate here. And then moving on to the retreat state. From the retreat state there are going to be three things that can happen. Either we have driven away from the line and we are done retreating, and then we should transition to the search state. So I'm going to call this finished. And further on, the way I'm going to implement this state is also as a set of substates, and in each of these substates they're going to represent a set of moves that needs to be taken in order to drive away from the line. First of all, it might drive back from the line, and then it might turn around and go back a bit more. Inside the main retreat state, the timeout is going to happen once it has finished a single move and has to increment to the next move. It's going to stay in the retreat state when a timeout happens. This is going to become more clear when I move on to the code later on, so just stay with me here. And then again, if I press a key on the I remote, I should transition to my debug state manual. Since this retreat state is a bit more complicated, I'm going to draw its details in a separate diagram, but so here I will just have a simplified version. So like this. And then finally, we have the manual state. If we transition to the manual state, I'm just going to stay in this state forever, and it's just going to react to a command event. If I regenerate this again, this is what it looks like. This should be named manual up here. So that's now. So this is it for the overall state diagram for this Zoom robot, and I'm going to reference this when I move on to the implementation. But before I do, I can just quickly also show you the diagram for the details of the retreat state. I'm not going to go through it entirely here, but I'm just going to show you the final version. Retreat state. So it looks like this. Depending on where the line is detected, I mean, the line we might be driving straight ahead and then detect the line on either sensor, either both of them or just one of them, or it might detect the line back at here or to the side. And depending on where it's detected, it has to drive in a certain direction. And I'm going to represent these different cases as different substates. This is what I'm trying to visualize here in this diagram. So I will refer to this actually in the next video when I implement the details of the retreat state. But I will just leave it like this for now. As I said, there are many ways to implement a state machine, but in this video I'm going to implement one in C. And I'm going to keep things quite simple and implement it with standard code constructs available in C. So it's going to be if statements, switch statements, and enums and structs. And I will handle everything sequentially in a big while loop. And there's not going to be any threads, events, or anything like that involved here. It's going to be a fairly simple implementation. And while this might not work for a more complicated state machine, I think it's a quite nice implementation for a smaller state machine like I will have for this project. And I will write it in a quite general way so that it's going to be easy to extend to have more states and more events. But first, let me create a new local branch to track the changes that I make in this video. Or before I do, I also have to mention a couple of commits that I made in preparation for this video. So let's look at the Git history here. One thing I implemented before this video was to improve my ring buffer implementation that I implemented in a previous video. Previously, this ring buffer implementation could only take elements of a single byte, and in the next video I'm going to implement a way to store previous inputs from my sensors in order to implement a more complicated behavior, because I will want this SumoBot to take into account, for example, where the enemy was last seen. In order to do this implementation, I will need to have a ring buffer that can take elements of different size. So that's why I extended this implementation. And then I have a second commit where I implement timer functionality. So first I implement a function called millis, which works the same way as the millis function in the Arduino platform. So it returns the number of milliseconds passed since the microcontroller was started. And I use this to implement timer functionality, which I'm going to use to be able to have the timeouts inside the state machine. So for example, I will need the SumoBot to be able to drive in a single direction for say 350 milliseconds. And to be able to do this, I will need to have timer functionality. So that's what I'm going to use this for. And interestingly enough, I implemented this by repurposing the available watchdog timer inside this microcontroller to be used as a timer instead of rebooting the microcontroller after some time. And I did that because I don't need the normal watchdog behavior in my Sumo robot, and the number of timer peripherals are limited on the microcontroller, and I'm already using them for other things in this implementation. So I thought this was a good idea. And finally, I made a small commit where I move all of my enum to string functions to a single file, just to make it easier to compile them out, because they take quite a lot of flash space. And what I'm going to show you in the next video is that I'm running out of flash space here. My microcontroller is quite small and my implementation is getting so big that it's taking up all of the available flash space. So in the next video, in order to compile my code, I will have to compile out some of the things that are not necessary, but only nice to have. And enum to string functions are just there to make the tracing nicer. That's it for the commits I did in preparation for this video. And if you want to see the details, as always, you can go to GitHub and look at the commits. And you can also clone the repository yourself and look at the differences. Anyway, let's now create the new local Git branch. And I'm going to call this feature state machine. I'm going to divide my state machine implementation into multiple files. First of all, I will have two files, a header file and a C file. State machine.c and state machine.h. And these files are going to hold the overall state machine logic. It's going to hold the different transitions and define these transitions, and also handle the input and translate these into events that can then cause the transitions. And then I'm going to implement the different states in separate files. You can just go ahead and add these different files immediately for the different states. First we have state wait, state surge and state manual. Then there will also be some data to be shared, or definitions to be shared between the different states, and also the overarching state machine logic. And I'm going to keep this in a file called state common. And this is just going to be a header file. And while at it, I can also add this to the make file. Beginning with the overarching state machine logic. This is just going to have a single function called state machine run in order to start the state machine. And this will start the state machine and keep it running endlessly. So during execution, when this function is called, it's going to get called once and we're never going to leave this function. I'm going to call this directly from the main file. So after I've initialized everything, which I also have to do here, then I will call it down here. And I also need to add the required headers here. That. Yes. Okay, so going into the implementation for state machine.c, begin with including header file, then state machine run. So in this function, what we need to do, first we need to initialize the state machine data, because there's going to be a bunch of data or state that we need to hold during the execution of the state machine. Allocate and initialize state machine data. Then a while loop, and in this while loop we should process the input. We're going to have a bunch of inputs: line, timeout, enemy, command, and whatnot. And this processing the input is going to take this input and turn it into an event, and then we should process this event in order to cause the transition. And beginning with the state machine data, I'm going to represent that as a struct called state machine data. This is first of all going to hold the state, which is going to be an enum that I'm going to define soon, and then it's going to hold the data for the individual states. So I'm going to define additional data structs for the individual states. Let's just sketch them out here for now. So first I will have one for common data. Yeah, and then I will have some additional things here, but I will just add a comment for here for now. Then I can head over to state common, where I'm going to have the different enums for the states and the events that can happen or that exists. And state manual, then for events. And here I'm also going to have the state common struct data, and this is going to hold a pointer to state machine data. Then it's going to have a timer or a pointer to the timer. Also enemy. This is going to contain everything that needs to be accessible within the individual states, or within all individual states, basically. The shared data. It's going to be the shared input. I'm also going to have a ring buffer for the input history. What all of these do here is going to become clear as I go about implementing this. So I'm just trying to just define everything right now. And then to keep this header clean, I will do some for declarations up here. And should have a comment, and also the necessary include, and include. That's it for the common header for now. And then moving back to state-machine.c, I can implement the struct for a transition. This is going to contain three things. First, it needs to hold the state which the transition is going to come from. So that's going to be from. Then it's going to have the event that's going to cause the transition. And finally, the state we are transitioning to. And then I can create a big static const table to hold all of the possible transitions. Here it's really just a matter of filling in the corresponding transitions that I drew in the diagram. If we refer to the diagram again, we're going to have a bunch of different transition and events. So I'm just basically going to fill in the possible transitions here. So these are all the possible transitions. And as you can see, having it defined in the table like this, it's going to be easy to add additional transitions if I want to, which makes the state machine easy to extend when you implement it like this. And then I can have a comment up here that also gives a tip about looking at the diagram to understand where these transitions are coming from. Then I can implement the function that's going to take an event, and then that's going to go through this state transition table in order to find the corresponding transition. And I will make this inline, since this will only be called in a single place, just to save the function called overhead event. So it's going to take two arguments, and that's going to be state machine data, which is going to contain the state we're currently in, and then this event that we received. And inside here I need to loop over the available transitions size, and then I should have an if statement that checks if it is a match or not. Transitions I dot from and next, that should be called next event. And if next event equals state transitions event, and if it is a match, we should enter this new state. So I'm going to call state enter, which is going to be another function I need to define, and this is going to pass data and state transition next event. I guess I could pass the entire or point to the transition as well, but well, I will just do it like this. Then I can return from this function. And if we don't find a match, this shouldn't happen, because in the state machine or state transition table, I should cover all of the cases. But in case I miss something, I should trigger an assert down here. Then I will have static void state enter state machine data 2. Inside here I should just call the corresponding enter function depending on the state that I'm entering. So for each individual state I will have a function called enter to enter this particular state, but let's implement this a bit later. And continue with state machine run here. To allocate and initialize the state machine data, I'm going to allocate this data on the stack. Just because in this case I think that's a bit nicer. I like to allocate things on the stack whenever I can, instead of like making it statically and globally accessible. And then I just pass it as a pointer in each function instead. And then I will have a function to initialize this data struct, and endless while loop. I'm gonna take event, and then that's going to come from process input function. And when I have the event, I can call process event, which is the function that's going to cause the transition to another state if a particular event has happened. And another thing I'm going to add here is a delay, which I don't need for when I'm running it on the actual microcontroller, but for my simulation I need to have this. And that's because in the simulation I'm going to run this in a separate thread, and I need a way to sleep in this thread so that it can execute the rest of the simulation. But you will see what I mean in the next video when I actually simulate this code. It's going to be state machine init, and it's going to take struct state machine data. Make this in line as well. First I'm going to set the initial state, which is going to be state wait. Then I can set all of the things inside, or let's see if I can open up the state common here to begin with. Okay. First set state machine data inside here. So that's just gonna be data. This is gonna be common. Enemy position. Going to initialize these to default values because they are going to be, or I'm going to set these when I process the inputs. That. Then I can also set, and that's going to point to the timer I'm going to allocate in this data overall state machine data struct. I should clear this timer. This is what I implemented in preparation for this video. So I can just quickly show you. So it's this interface right here. And I'm also going to set two other things here. I need to handle something called internal event, which I'm going to explain soon, and input history, which I'm not going to implement in this video, but in the next video. And the input history is just going to be the history of previous inputs, which I'm going to implement with the ring buffer. And then I can set the common data for all of the individual states, and also call their corresponding init functions. The wait common is going to be equal to data common, pointer to data common, search common. And I'm not going to have an init function for all of the states, only for search, attack, and retreat. Yeah, yeah, and then I can continue with maybe filling out this state enter a bit more. I'm going to switch across the state we are transitioning to, and then I'm going to have a case for each individual state, and simply call the enter function for each state. And as you can see here, I use a switch statement without a default case, which means I will get a compile error as soon as I add a new state, which is nice. And when a transition happens, I also want to do some additional things. First, in case there is an ongoing timer, I want to reset that timer so that if I transition from a state that started the timer, I don't want that timer to trigger timeout in the next state. And I also must update the variable holding the current state. And finally, I'm going to trace here. So from to then event that caused the transition. And here I'm going to add some enum to string functions, state to string, state to string 2, and then I can go to my enum to string functions and add these new functions. And in here I can, and then the next one like so, and going back to state machine .c. That's it for this state enter function. Then I should also implement the process input function. Line void process input. And most of this function I'm going to implement in the next video. I'm just going to add a few comments or to-do comments here. Make this unused for now. The first thing we're going to do in this function is get the input from the sensors. It's going to be enemy, IR remote, and the line. And I should save input to history. Then I'm just going to have an if statement going through the different things or inputs that can happen and return a corresponding event. If remote command, then should return the event command. Else if it's an internal event, which I'm going to talk about soon, I'm going to return the internal event. And if a timeout happened, should return the event out. And I'm doing these if-else cases in a distinct order here from the most important ones to the least important ones. For example, if multiple things has happened, the remote command should always take precedence. So even if I have detected an enemy, I should process the remote command because that's going to transition to the manual state. And when we are in the manual state, we're not going to care about any other input. Line detected, then return date event line. And if enemy detected, return state event enemy. And if there are no input, I will just return state event none. So let's now add the functions for handling eternal events. And what I mean by an eternal event here is events that can be posted from within the states themselves. For example, in the retreat state, there's going to come a point when all of the moves, the retreat moves, has been executed. And when that's done, it's only going to be known inside the state retreat. So we need a way to be able to post events from within the states themselves. And that's what I mean by an internal event. We're going to need a couple of functions for this. First, one function to post an internal event, and that's just going to set internal event to event. And I can add this here too. And I'm also going to assert here to see that there is no pending internal event, just as a sanity check. Internal event turn none. And then we need a function to also remove an internal event when we're handling the internal event. Call it take internal event, return value state event. And here we can also have an assert to check that there is an internal event. Then we can get the internal event and set internal event to, and then finally return event. That. And then I'm going to have the declaration of this function be inside state common so that all of the states can access this function. Inside here, you can also add a comment above. And then I can go ahead and add timer here as well. And I will also have buffer input history. Remove that comment. And if I don't use this function now, I'm going to get a compile error. So until next video, I will just add this as an empty call basically. So like that. Okay. And what I'm going to do now is implement the individual states, or at least implement the skeleton code for the different states. And before I do, what's important to understand here is that for this implementation to work, I must be running these while iterations very quickly, because if any of the code inside here blocks, that means that it's going to take a long time before we process the input, because the input is only processed once for each iteration. For example, if one of the states has some blocking code, so it waits for maybe half a second or a second, that's not going to work, because then we're not going to process the input fast enough. Because in order for this to work, we need to, for example, these surrounding sensors here need to be able to detect the line as quickly as possible, ideally within 10 milliseconds or less. When I implement this, I need to make sure that all of the code is just executed in a sequential manner and doesn't block anywhere. And this further means that when there is nothing happening, I will still be iterating through this while loop, but the only thing that's going to happen when we don't get any input is that we're going to return event none here, and that's going to be processed, and most of the times that's not going to do anything. But that's just a way to keep this while loop executing, so we keep on checking the inputs. Okay, before I get to implement the individual states, let's just add a comment that explains what I just told you. What I've written here is just basically what I just explained. No code inside the state machine can block, because otherwise this approach doesn't work. Note, not being able to block for a certain duration of time doesn't prevent me from executing actions over a certain amount of time, because instead of blocking for a certain amount of time inside this process input, I'm simply just going to check repeatedly whether the timer has timed out, and that's going to give me the same behavior. Okay. Starting with first state, state wait. I will have state wait enter. That's going to take struct data event. Then I'm going to define the struct that's going to hold the data that this state needs. To be very simple, it's just going to have a pointer to the common data. I need to add the necessary include. Start signal, remote command. And inside the implementation file, include void there. And here I can begin with an assert, just for sanity checking, because we should never enter this state from any other state. So I can just say state wait here, and then that's going to be it for this function actually. And that's because when a command happens, we don't need to handle it here, because that's going to be taken care of inside the overall state machine code, because that's where we process the input. And when we get an input from this remote control, it's going to translate to a state event command, which is going to cause a transition. And then I'm going to add a comment above all of the entering functions, just to make it very clear that no code can be blocking inside these functions. And I'm also going to add another clarifying comment here, because what this state is currently doing is not how it should behave in an actual SumoBot competition, because then it's not going to take the input from a remote control like this, but instead take the input from some other IR transceiver. But I'm not going to implement that in this video series, but the approach is still the same. We're going to get something from an IR transceiver, and this is an IR transceiver in a way. That's all there is to the wait state, so very simple. And moving on to the search state, it's going to be a bit more complicated, or I shouldn't forget the necessary includes here. Need assert and then state search. Define state search. So the structure in all of these state files is going to be very similar, and this also means that it's easy to add additional states, which is kind of the idea with the way I implement this state machine. Once again, we're going to have an enter function, and that's going to take a data struct that contains the data specific to this state, and from state event to. And for this state, I also need an initialization function. And in the data struct, there's going to be two things. First of all, a pointer to the data common to all state. And then since the state search is going to have internal states, it needs a variable to keep track of which states it's currently in. I'm going to have another enum for this. Search state. So these are the two internal states that I showed you in the diagram before. So that's state search rotate and search state forward. And I need to include state common here. Then I need to comment what this state is supposed to do. Drive around until enemy is found or line is detected. And then inside the implementation file, I need to implement these functions. Include void the init function, and here I'm just going to set the initial internal state. That's going to be search state rotate. Then inside the state search enter function, comment on top here as well. Here, as I'm going to do in most other enter function, I'm going to add a switch statement across the possible state we may have come from, and then inside I'm going to switch on the different events. And these are also going to be switch statements without a default case, so that when I add a new state or a new event, I will get a compile error, which is going to make it easier to remember that I need to handle the event or state in each individual state. From here is going to be the different state. Wait, hack, search, treat, manual. And for state wait, the only way we can get to from state wait is if a command event has happened. So let's add an assert to sanity check this. And then I will have another function that's going to set the actual drive that corresponds to this internal state. I'm going to have a function called state, or an internal static function called state search run break. And then the attack and retreat state is going to be handled the same way. So I will just fall through here. Inside here, I'm going to switch across the event. There is a bunch of different events. And for timeout, line, and enemy, that should never be a reason for why we transition from retreat to search. So I'm going to assert here. And if state event none from a state retreat, that should also never happen from the retreat state, but it can happen from the state attack, because that means we have lost enemy and transitions to state search. So I'm just going to add a sanity check here for that as well, just to make sure that we're coming from state attack. And then I'm going to fall through here and do the same as if we got a command, or that's also going to be down here. And then I'm just going to call state search run here as well. Break. And if state event finished happens, that means it must have come from state retreat. And in that case, I should also call state search run. But here I also need to change the state in case we are currently driving forward, just to make sure that if we're going back and forth between searching and hitting the surrounding edge border, I should change the strategy so that I don't end up driving forward all the time. Now it's hard to show you why this is a problem, but otherwise this robot can get into a state where it's just driving back and forth, detecting the line, driving back, detecting the line, driving back. Adding this if statement here, make sure that I break out of a case like that. And here I'm also going to assert, or for state manual I'm going to assert, but then I also need to handle the state search case. And similarly, I switch across the possible events. If I get event none here, we are in the search state and nothing has happened, so I shouldn't do anything here. And as I explained, this is just to be able to keep the state machine iterating so that it can process the input. And then for all of these below here, they should not be possible, so I will assert. And the only one that's going to be possible is the timeout. And when a timeout happens, I should switch to the other internal state. I can switch across the internal states. Case search rotate and case search state forward. And I'm going to change the state opposite state. It's going to be forward. Below here is going to be rotate. I just call the regular run function in both of these cases. Like that. Well, I could move this down here instead. And then I can go ahead and implement the run function. Now I'm not going to implement this function fully, because to implement this fully I need to have the input history in place, because when I decide which direction to rotate, I want to check where the enemy was last seen, which I need to use the input history for. Seen, but going to switch data state, internal states, word. Break. Okay. For now I'm just going to start the timer, and then I'm going to have a define. For the duration we're going to stay inside this state. This. I set this to 1000, and the reason I'm setting this to 1000, or this is in milliseconds, so that's going to be 1 second, is because I've tried running this code on the actual robot, and I find with the speed that I'm running at, 1 second is good duration for this. And I'm also going to have a timeout for the other state. I'm going to set this to 3 seconds, also based on my experimentation. And here I can also set the drive, so I'm just going to drive forward, fast, and then also start the timer. Then I also need to include some additional things here, and also assert. Okay, this is all I'm going to do for the state search in this video. That's going to correspond. You can just open the diagram here again. It's going to correspond to what's happening inside here, inside state search. We're going to transition between these two states here. Either we are rotating or we're driving forward. And we might get to this search state for different reasons from different states, as you can see in this diagram. And that's what I've been handling inside the code here. Now I'm going to do something similar for the rest of the states, starting with or moving on to state attack first. Once again, everything follows a very similar pattern. Going to have a init function, and I'm going to have an enter function. This is going to take struct state attack data as argument, which is the data struct that's particular or holds the data specific to this state from, the state we came from, and the event that caused the transition. Here I'm going to have a data struct, and this is going to contain a pointer to the common data, and also hold a variable to keep track of the internal attack state, because the state attack is also going to have internal states. It's going to have 3 different states. I'm going to represent that as an enum called attack state. Type def this enum up here. Attack state forward if we detect enemies right in front of us. Attack state left if the enemy is slightly to the left, and attack state right if we detect the enemy slightly to the right. And then include app state common, and also a small comment, drive toward enemy detected enemy. Then switching over to the implementation file, include, and beginning with the init function. That's just going to set the initial state, and then I can go on to the enter function. Here I'm just first going to get the next internal state, which is going to be based on where we detected the enemy, and I'm going to have a separate function for that called next attack state. That's going to take enemy as an argument, and I will also need to keep track of the internal state that we left. And then I'm going to switch over the states we may have come from. I'm also going to add a comment on top of this function like the other enter functions to remind myself that I should not have any blocking code inside these functions. And then I'll switch over the events. And the only reason we can go from state search or from searching to state attack is if we have detected the enemy. Here I'm also going to have a state attack run function break, and if we got here for some other reason, that should not be possible, and I'm just going to add an assert here for sanity check. And if we came from state attack, it means we are already inside attack state. And if we detected enemy again, it might be that we detected enemy in another direction, and in that case we might have to change the way we are driving. I'm going to check if the previous state is the same as the current state, and that's why I save this variable up here. And if that's the case, I need to run the state attack run function again. And if not, I'm not going to do anything and simply drive the way we are currently driving, because we are already inside the attack state. And it will also be possible to get the timeout while you are in the attack state. It might be, for example, that we are head on to the other enemy and we're just like, maybe they are driving in the same speed, so they're basically at a standstill. And I'm going to have a timeout to detect this case, but I'm actually... like, it would be possible to kind of implement a breakout strategy to handle this case, but I'm not going to do that. And instead I'm just going to have an assert. I will still have a timeout, but I will assert when the timeout happens. And I will have a to-do here, a breakout instead of asserting. And for all of these other events, we should never be in the attack state and get this event and then process it here again. This is not possible. There are no state transitions for this. I'm going to assert as a sanity check. We should never go from state retreat directly to state attack. We should always go past state search first. I should just assert here, but I will also add a comment, break. And it's also not possible to go from the wait state or from the manual state to state attack. So this is also an assert here. Then I can implement this next attack state function. Here I'm just going to have an if statement going over the different directions the enemy may be at. This is not possible. So if enemy at front, I should return attack state forward. And if enemy at left, left. And if right, attack state right. Then I will have the state attack run function. Attack data as an argument. I will switch over the internal states to handle each individual case. Case attack state left. I will set the drive if it's in forward, or if it's in front, I should just drive straight ahead. So that's going to be drive direction forward, and I will use fast, so drive at a fast speed. And if to the left, I will do an arc turn to the left. Similarly, if to the right, I will do an arc turn to the right. And then I will have the timeout I talked about. Start, time, data, common, timer, state, timeout. Define timeout. I'm just going to set that to 5 seconds. Then also add the includes that I need with drive, timer, and the assert handler. Okay, that's it for state attack. Moving on to the next state retreat. Same pattern again. State. And I'm gonna have a state init function. So state retreat init to initialize the internal state data. Enter, struct, state. And so first the common data, or a pointer to the common data. And then there will be a bunch of internal states for this state as well. And as I said, each retreat state is going to correspond to a set of distinct moves. And we need a variable to keep track of which move we are currently at. So that's just going to be an integer move index. And then an enum2 for all of the internal states. There's a bunch of these states, these ones. And that's it for the header. So moving into the implementation file, include app/state retreat and begin with the init function. So here set the initial state, and here it's also important that I set the move index to 0, since this data struct is going to be initialized on the stack, which means that the initial value, or it's not going to be 0 initialized. We need to set 0 explicitly here. Then I can do the state retreat enter function, add the usual comment on top, and switch across the different states we may have come from. And whether we came from the search state or the attack state, that should be handled in the same way. So here I'm going to do a fall through. It should not be possible to come from the wait or manual state. As a sanity check, I will assert break. So inside here, I need to switch over the possible events, and the only reason for transitioning from search or attack to retreat is if we have detected line, and if we got any other event, that should not be possible. There is no transition for that, so I'm just going to assert as well. Then I'm going to have a separate search run function, similar to what I had inside state attack. And if we are already in state retreat, it means we are currently driving away from the line, and it might be that we need to increment the current move we are at. So let's just switch over the possible events here as well. So if we detect the line again, that means that we have detected the same line, or that we have detected some different line position, and this means that we should just start over. So I'm just going to call search run. Otherwise, if we got a timeout, it means that we are done with the current move and we need to increment the move index. Increment move index ++. And then I need to check if this retreat state is done, because then we need to leave this state. And here is where I need to use the internal event functionality. I'm going to post internal event. So common state machine data and state event finished. I post this state event finished here because the retreat state is the only place where we know whether we are done with this state. So I post the event here, and then inside the overall state machine logic, I'm going to pick up this event and transition away from this state. But if we are not done, then I need to start retreat move, which is another function I'm going to implement. Then these two, finished and command, should not happened inside, or it should not be in retreat state and handle these events inside here. So that's going to be an assert. But it's fine to detect the enemy or to not get any event at all. So then I'm not going to do nothing. Enemy retreating. Okay, so let's implement the helper functions. Retreat run. This means that we are starting a new retreat state. So we should set move index to 0. And we should set the state to the next retreat state. We have separate functions to decide which retreat state we should use based on the where we have detected the line. And then we should start retreat move. Then I need a function to check the current retreat state is done. It's going to be a matter of checking whether we have reached the maximum move index for this particular state. I'm gonna have a table for these individual states. So I'm just gonna write it like this. And then a function start a retreat move. Assert first that move index is less than the maximum amount of moves inside this state. Then I'm gonna get the move based on the index, the move index. Then I'm gonna start a timer and set it to the value for how long this move is going to go on. And then finally set the drive for this move, so the direction and the speed. And then I will have a big table to define all of the different states and the moves inside the states. I'm not going to fill this in completely now, but instead do that in the next video. But I will still create a table here in this video and add one move at least. Reverse. Each of the states is going to contain the number of moves and the information for each move. So that's going to be the direction and the speed and the duration. So if we are in state reverse, we should be driving backwards at maximum speed and timeout of 300 milliseconds. Rest, which I will do in the next video, as I said. And then we also need the find the struct for a retreat state. Moves, and then move count. Struct to represent the move, duration. Define count. None of the states is going to have more than 3 moves, so I set this to 3 here, just to reduce the amount of flash space this table requires. Then I need a function to check the corresponding internal retreat state that we should enter. And here I'm going to switch over the line. And there are many ways we can detect the line, and I'm not going to implement this function fully here, but do it in the next video. But I'm going to write some of the code at least. But when I detect the line to front left, I will need to do some more checking inside here to decide which retreat state to enter, just to get a smarter behavior. And that's also going to be true for this other state, and also for this one, and for front. But if we detect it to the back, that should just be return retreat state forward, and if left, return state right. This should be our turn left, and if diagonally left or right, I'm actually going to assert here for now. This can happen, but it happens rarely and it's a bit ambiguous, so I would need to have some more complicated code for doing something smart here, and I'm not going to do that in this video series, so I will just add a comment. And if line none, I will assert, because then we shouldn't have called this function. And we should navigate to here, but for the compiler to not complain, I need to return something, so I will just return reverse. And later on I will also need a function to get the current move, but I will just add this function here for now and not actually use it, but I need to call it from somewhere, so I don't get the compiler, so I will just call it here. And then includes that we need. So there's going to be a lot going on inside this retreat state. It's the most complicated state, but overall it's similar to the other states in a way, at least the structure. And then I can go to the final state, state manual, and do the same for this one. So state manual. So a lot of dry coding in this video, unfortunately, but I promise I will be showing that everything works and how it works in the next video. In this video it's more about just crunching out this skeleton code here. So this is going to be quite a simple state. There's not going to be any internal states. This is just going to be a manual, have an enter function, and a pointer to the command data. And inside the implementation, I will first include a manual enter function, same command above. And then I'm not even going to check which state we came from. If we got an event that is not state event command, we should just do nothing and return. And then I can switch across the possible command. So if we got a command or pressed up, we should drive forward. If down, we should drive rotate left. If right, we should rotate right. And if we got something else, we should stop. And if you got none, we should do nothing. Then we need to add the includes common define stage. Okay, so let's now finally see if we can compile this code. Probably going to have a bunch of compile errors, so let's just try to build this first. Build for the SummoBot. Oh, yeah. Here I need to include common.h. Yep, that should be common. As you can see here now, even though I haven't even fully implemented the state machine yet, I am running out of flash space, because as the compiler or the linker tells me here now, the ROM has overflowed by 134 bytes, which means that I've taken more than 16,000 bytes. So what I need to do now, I need to, since that was the reason I moved all of this to a separate file, so that I can pass this define here in order to disable the enum strings. So I'm going to do that inside the make file. That here. Clean. Oh yeah, and then I also need to add empty defines for these ones here. It kind of sucks that I'm running out of flash space, because that means that when I have the final implementation in place, I can't really run it in full debug mode with full tracing on, and that's a bit annoying. The entire reason for this is that I picked a microcontroller that is too small for this implementation. Just having maybe the double amount of flash space would have given me much less headache. Define state. But oh well. Okay, so now it compiles. So let's also run format and CPP check. Let's also run the build script or the build all test to see that that also compiles. Okay, now I think I've written all of the code that I want to write in this video. As I said, unfortunately, I'm not going to test out the code in this video, so it's just a lot of dry writing of code. But in the next video, there will be more testing on inside my simulator and also on the actual robot to make sure that this code works. Now I'm just going to commit this code. I will add all of the changes. Add new, add docs, add source app. Create a commit. Video 25. That, and then I can push this branch. That's gonna be origin state machine. Then I can just make sure that this actually pass my CI system as well. Create a pull request. Yeah, and all checks passed, so I can rebase and merge. Okay, so that's all I'm going to do in this video. There's been a lot of coding in this video. I've written a lot of code that I haven't actually tested yet, but this video was mostly just to sketch out the overall structure of the state machine code. And I wanted to show you like how you can write a state machine in C, a simple state machine in C, in a more general way, so that it's easy to add new events, transitions and states. And then in the next video that I'm going to make, I will implement the details of this state machine to get the full behavior of this SummoBot, so that I can actually first simulate the behavior before moving the implementation to the actual robot to see that it actually works. And this also means that now I am getting to the really end of this video series. It's actually just going to be the next video and then a final video to sum everything up. So thanks for watching and see you in the next video.